Okay, so this is section 7.3, and it is on solving three variable systems. And we're going to use matrices to solve them eventually. I'm going to show you the methods of solving by hand. And they're a little tedious, but they work. The first one's not going to be bad because of the nature of the equations. We're going to use substitution on this first one. Okay, so this one, they were nice and they gave us z equals 3. So I'm just going to plug in z. Now I'm going to do the second equation because that when I plug in z, I only have one variable. Y plus 6 equals -7. Y equals negative. Oh, I don't know why I plugged in -3. I'm ahead of myself. That's not negative. It's +3, and that makes it -6. I'm going to add 6 to both sides. I'm going to get y equals -1. Now I will take my first equation and plug it. I don't know what I'm doing. I'm not thinking this morning. I'm going to plug in my y and my z. Actually, let's combine like terms on the right left side first. So this is +3 plus 3 is +6. I will subtract 6 from both sides and get 1. So that's not +6. I am struggling this morning. So -2 times -1 is 2 plus 3 is +5. There we go. X plus 5 plus 7. Yeah, I looked at the book. It's going to help me get it right. So I know this. This three variables could be represented with three-dimensional coordinates, which are written like this, x, y, z. Okay. That's method one, substitution. And anytime you have a variable given to you, always substitute at least that part. This was nice because their second equation only had 2, so substitution was really nice and quick for that. This next example, we're going to use Gaussian elimination. Gauss is after Carl Friedrich Gauss, a German mathematician generally considered to be the greatest mathematician of all time. He lived in the 1800s. We will talk about Gauss's formula in chapter 9. This guy was highly brilliant. This time I've got 3 equations and 3 variables. Anytime I'm solving a system of equations, I must have as many, I guess more as possible, but as many variable or equations as variables. So since I've got 3 variables, or sometimes we'll say 3 unknowns, I need to have 3 variables. So when doing this, I'm going to go ahead and let's combine the first 2 equations. We're going to do linear combination or elimination. Let's try to get the x to cancel out. So I'm going to multiply the top equation by -3. And I'll put it over here. And then I will take the second equation, I'll put it underneath, and I'll add them together. So just like I've done elimination in the past, and like we did with 2 variables in 7.1, except this won't give us an answer. So the x's cancel out. Negative 3x plus 3x is 0x or 0. So I'm not going to write it. 6y plus negative 5y is negative y. I intentionally chose negative 3x so I could just add them together and lose the x's. Negative 3z plus z is negative 2z. Okay, I've got one equation with two variables. I need to take another combination of the three equations and make another equation without an x. So I need to get rid of a variable. I'm not sure why we didn't just do z. If I had done this without looking at the book, I would have let z's eliminate. I would have added equation 1 and 3, and z would eliminate at 2 and 3. But I looked at the book, and they chose to eliminate x. So either one works. Z probably just would have been slightly easier. So I need to eliminate x, though. Even though z would eliminate really easily, that would not get me to an equation that's going to match this one with y and z. So now I'll multiply the top one by negative 2. That's going to give me negative 6x plus 10y minus 2z equals negative 28. And positive 6x minus 6y minus 3z equals 9. And when I add them up, I get 4y minus 5z equals negative 19. They added different equations, so they have a different result. So now, and put these two equations together. And I guess I will multiply the top one now by negative 4. And bring it down here, and I'll add them together. When I add these together, I get 3z equals 9. Z equals 3, and that is correct. Now I will take one of my YZ equations, probably the one with the blue arrow next to it. So this one again. Doesn't matter which one, but that one is just Y. And I'm going to plug in my Z. So now I'm essentially working my way back with substitution. Y is equal to negative 1. Now I'll take one of my originals. How about the top one? From the original. And actually, I think we get the same result as before. The top equation is exactly the same thing. It's going to be x plus 5 here equals 7. When I subtract 5 from both sides, I get x equals 2. So 2, negative 1, 3. And yes, we do get the same results as example 1. We just had slightly varied equations. I guess that's maybe why they eliminated x. Again, I would have chosen to eliminate z's here. I would have gone this route. First and third adds up to have the z cancel out. Second and third adds up to have the z cancel out. Okay, we're going to do one more with Gaussian elimination. And it is possible that these don't all intersect. This XYZ is actually in 3D space. It's not the graph of a line, it's the graph of a plane. It's a flat surface cutting through 3D space. let's say here, my surface of my folder is flat, it cuts through 3D space. Could be tilted like this or like this, depends on the values, the coefficients of in front of the X, Y, and Z. But those are all planes cutting through space. This is example 3. It is possible to have parallel planes. So I have my 3 equations here with my 3 unknowns. I think I want to get rid of X, and I'm just going to start with the first 2 equations because they're just ready made to get rid of X. And again, I chose X because I thought the numbers were the easiest. Oh, hold on. I've got something really messy, probably hard to read. That's not a B, that's a 13. Okay, back to my equations. Adding them together, I get negative y minus 4z equals 7. There's one. It's a good place to start. My second one, I'm going to do 2 and 3 because I want to do 2 and 3. Then I can multiply by a positive. I could multiply the bottom one. I can't do 1 and 2 again, so I have to do something else. Negative 5x plus 10y minus 25z equals 15. When I add these together, I get negative 3y minus 12z equals 15 and 8 is 23. Just want to make sure I copied that right. Okay. So now I bring these 2 equations together. And I'll do linear combination on these. If I multiply the top one by negative 3, I will get something that I can get here to cancel out. So negative 3 times negative y is positive 3y plus 12z equals negative 21. When I add these together, I get 0 on the left side and 2 on the right side. This is not true. Anytime I'm doing elimination or substitution for that matter, and my variables cancel out, if I get something that just isn't true, and I say that's false, then I know I have no solutions. And in 3D space, this is going to basically represent we have parallel planes. So what I have here in 3D space is I have plane, a plane, and some other plane. They're going to intersect. If I have a solution, they intersect at one point. If I don't, I have at least 2 of these planes are parallel. Okay. And I have some intersection lines, but 2 of these planes just aren't going to work together. They're just not all going to intersect at a single point. Actually, I guess they might not. It's possible that the planes could just intersect in different places. There's not a single point of intersection, though, for these. Okay. So we're going to take these now and we'll go to a slightly different equation. And then we're going to put them into what's called a matrix. Now, we've introduced matrices before. And we're going to put them into a augmented matrix, it's called. Okay. I'm going to show you how to do that. I'm going to show you how some places write it. And it's sometimes a little easier to write than with your book. The way your book does might be a little easier to see. I probably wouldn't always write it this way, but I usually use the method 2 for solving with matrices, not the first one. The first one I think is easier if you have to do it by hand. And you will have to do it by hand using a matrix for some of them. So what we do is we take our coefficients, 1, -2, 1, and then our 7. This is actually going to be a 3 by 4 matrix. And what's sometimes put in here is a little vertical line here, separating my coefficients from my solutions for each equation. And so this is my augmented matrix, okay? And if you look at the book, you'll see they took these equations, and yes, they had simplified them down to where the point where you end up with these, this is what we got when we solved example 2. We had this equation at one point. And this is going to lead to what we're trying to get to, which is a row echelon matrix or a reduced row echelon matrix. So this one right here is a row echelon matrix. I'm going to talk about what that actually means. And the key here is these parts of the matrix. Row echelon form. And the key here is I got down to Z is 3. And I could essentially replace that bar with all these are equal signs. This is 1x. We don't write the x, y, z in here. But that's what we've got going on here. So now I've got z equals 3, and I can use substitution working backwards. Row echelon form has 1s down this diagonal and 0s in the lower left corner. Well, reduced row echelon form, which is where I kind of ultimately want to get to, is going to turn all of these into zeros. And we're going to use matrix operations instead of Gaussian elimination to get there. You might find this worse. It's really nice when your calculator does it. So I'm going to take a new example, and I'm going to take 3 equations. X minus y plus 2z equals -3. I think if you did this a lot, which I've never done it a lot by hand, I think if you did it a lot by hand, it would end up being easier to do with matrices. So we're going to put that into a matrix. 1, -1, 2, -3. 2, 1, -1, 0. -1, 2, -3, 7. And there's my matrix. Okay. My goal, so let's first go with, we're going to turn this number right here into a 0. And I'm going to accomplish that multiple different options. I could multiply row 3 times -2. what I can do is I can multiply any row by anything and add it to another one. So what I'm going to do is -2 times row 1 plus row 2. What that does is -2 times row 1 is going to be -2, 2, -4, 6, +6. And I'm going to add it to row 2, and I'm going to place it into row 2. 2, 1, -1, 0. When I add them, I get a 0, 3, -5, 6. So what that looks like in my matrix, I'm going to bring it down to here. Row 1 and row 3 don't change. I've simply placed my new solution that I just got from adding those into this line. I don't always write them out. So now, next thing I need is we're going to turn this next one down here into a 0. So we're going to work our way over with get our zeros in place on this column because it's easier to add when we have zeros to get the next parts. So right here, I'm going to add just R1 plus R3. Not B, R3. And I'm going to stick that into row 3. That means I don't change row 1 or 2. Part of the trick on this is 1. So I'm going to just add them up. 1 plus -1 is 0. That was my objective. The rest of it has to be how it goes. -1 plus 2 is 1. 2 plus -3 is -1. -3 plus 7 is 4. So my objective, and we're going to go all the way to reduced row echelon, is to get something that looks like this. And then I'm going to call it X, Y, Z, and those are my solutions. Once I get there, because this really represents 1x plus 0y plus 0z equals something. 0x plus 1y plus 0z equals something. 0x plus 0y plus 1z equals something. And I called them x, y, and z over here, but maybe I should have called them A, B, and C. So now I need to turn this value right here to a 1. To do that, I need to do it with 2 and 3 so that these stay at 0. So the first ones stay at 0 only. Okay, so I'm going to turn that into a 1 by R2 plus 3 R3. No, not +3, -3. I'll make that a meter 3 while I'm at it too. Guess I erased more than I wanted. -3 R3. So I'm going to fill in the rows that I'm not changing. Well, I know that's going to be a 1. Here's the other one I'm not changing. I set that one up to be a 1, but R3 becomes, term is here is 3 and -3 is 1. 5 and -3 is -8. 6 and negative 12 is negative 6. Oh, that works. Oh, here's an easier one. The book did something easier. That would work. Not as easy as it can be. You can also swap rows. So because I have a 1 down here, because this right here is a 1. So matrix operations, you can add any rows together. You can subtract any rows. You can multiply them by a single number, like we've been doing with the -2 there. I can also swap rows. And again, because these are essentially x, y's, and z's, this works just fine. There's no magic order to which way I put the equations in. So now the next part I need to do, get this to a 0. Again, I better use R2 and R3 because of the zeros in these spots. If I use a 1, I might change one of those zeros into something not a 0. So I'm going to do -3 R2 plus R3. And this means, coming back over here, row 1 and row 2 aren't going to change. Oh, that's going to, this goes into R3. Forgot to write it by R3, but so -3 R2 is -3 plus 3 is 0. Good, that worked out to be what I wanted. -3 times -1 is +3 minus 5. I'm looking at this right here. -3 times -1 plus -5 is +3. That's -2. And -3 times 4 is -12, and -6. Okay, one more thing to get to row echelon form. And I'll keep going to get to reduced in a second, but I need to turn this value right here into a +1. I think I'm going to do that by -2 times row 1 plus row 3. No, I can't do that because it's not going to keep my 0. What I can do, oh yeah, this is easier. -1/2 times row 3 is going to go into row 3. I have to just operate on row 3 because of my zeros. So otherwise, if I add something to it, I'm going to change this number to a non-zero, and that's not going to be helpful. First 2 lines don't change. Yes, this is a lot of writing. 1/2 is 1. -1/2 times 6 is 3. So now I'm in row echelon form. I could say z equals 3 and plug that in for my next equation, working up y minus z equals 4. But I'm going to keep going to reduced row echelon form, which means changing these 3 to zeros. And the first thing I'm going to do is I'm going to try to get a 0 for this guy. And I want to keep row 1 because I need this 1 right here. So row 1 needs to be part of it. I'm just going to add R2 and R3, or R2 and R1, and put it into row 1. So my new matrix R2 and R1. I get a 1 plus 0. -1 plus 1 is 0. 2 plus -1 is 1. -3 plus 4 is 1. That's kind of nice. That one might make our life a little easier. 1, -1, 4, 0, 0, 1, 3. So now I want to take, there's a little trick here because I need to keep this one 0. I need to add something that has a 0 there. So it's got to be R3. And if I multiply R3 by -1, I will get that. So I've got R1 again plus -1 times R3. And that's going to go into row 1 again. That's 1, 0 plus 0 is 1. -1 times R3, so -1 times -1, or times 1 is -1 plus 1 is 0. That's what I was trying to get there. -3 plus 1 is -2. Again, rows 2 and 3 don't change. Now to go to row 2, I can just add row 2 and row 3. Because I need one more 0. It's going to go into my middle row. Top row doesn't change. The middle row becomes 0, 1. -1 plus 1 is 0. 4 plus 3 is 7. And row 3 doesn't change. So what does that tell me? Remember, my first place is it's 1x equals -2. 0x plus 1y equals 7. Z equals 3. And that is using a matrix. That's pretty tedious at first. It takes some getting used to. It's key that you don't add things when you need a 0 or stuff to go away. You're adding the correct rows. If you add it up and it doesn't work, just cross it out, go back and try it again. This will take some practice. But that is reduced row echelon form for matrix operations.